let's build an implementation of complex numbers. So here's an interface for complex numbers. All complex numbers should have real and imaginary components, and all complex numbers should have a magnitude and an angle, because they all are just vectors in this two-dimensional space. So I'm going to actually load the implementation that I will eventually show you, just so that you can get a feel for how it works. The idea is that I can create a complex number under either representation. I have two classes. One that is a complex number that stores a real and an imaginary component of a number. So here is 1 plus 1i. So if I look at C1, I see what I created is exactly what I typed in. We can also describe a complex number by its magnitude and its angle. So if we want to describe the same complex number, we're going to need to know how to compute square roots and what the number pi is. And then we can create a second complex number, which is described by a magnitude and an angle, where the magnitude is square root of 2 and the angle is pi over 4. So that's what Z2 is. Now these are obviously different things because they're different classes with different attributes, but they share the same interface. So whether I look up the magnitude on Z1 or on Z2, I get the same answer. And likewise, if I look up the angle on Z1 or the angle on Z2, I get the answer. Same answer. And the same should be true if I look up the real or imaginary components. Now you notice a slight rounding error here, but effectively they are the same number. Okay, so we have two different representations, Z1 and Z2, for the same thing, and importantly, they respond to the same messages, where the messages are these attributes. The fourth message that puts them in common is the imag message, which gives us the same number in both cases. Using this interface, we can implement arithmetic on complex numbers. By complex arithmetic, I don't mean that the arithmetic is complex, but it's applying to complex numbers. So here's how you add two complex numbers together. You add together the real components of both, you add together the imaginary components of both, and that gives you a complex number represented as a real and an imaginary component. How do you multiply two complex numbers together? Well, actually that's quite different. You want to create a new complex number represented by its magnitude and its angle. The magnitude of the result is just the product of the magnitudes of the input, and the angle of the result is the sum of the angles of the input. These are the easiest ways to express addition and multiplication of complex numbers, but they happen to use two different representations in order to do it. So that's why we have two different representations in our system, so that we can express addition easily, multiplication easily, without having to worry about committing to one particular representation, when there's a more convenient representation for each of these two operations. Okay, so let's look at the actual classes that we use to implement this. The complex Ri class, which is a complex number represented by its real and imaginary components, takes exactly those two things on construction and stores them. The magnitude is computed as a property method, meaning when I look it up, it looks like an attribute from the outside, but internally, it's actually computing the magnitude each time we look it up from the real and imaginary components. And here, what do? Well, we use Pythagorean theorem to square the real, square the imaginary, add those together, and take the square root. So this property decorator says, every time you look up the magnitude on a complex Ri object, call this function and return its value as the value of that attribute, as opposed to returning a method. The angle between the x-axis and this vector, described by real and imaginary, can be computed with a built-in function that does exactly that. So this is the angle between the x-axis and the point xy. And finally, we have a reasonable string representation of these objects. How does the polar representation work? Well, we want it to respond to the same 4 messages. But we want to store the other 2 different components as actual instance attributes. So the magnitude angle version of a complex number takes in the magnitude and angle as input on construction and stores them as instance attributes, but then declares a property method, real, which computes the real component of this vector, which just takes the cosine of the angle, multiplies it by the magnitude. And the imaginary component is the sine of the angle, multiplied by the magnitude. So these are basic trigonometric functions and exactly what they do. And we want a repr method for this. Okay, this is a complete implementation, exactly what was in the file that I loaded earlier. So when I create a complex number, from its interface, I know that I can access any 4 of the messages that describe its vector representation: real, image, magnitude, angle. Either of the complex number classes that I've created will work in the same way. And therefore, I define addition and multiplication without assuming that either one of these is of a particular class. Either one could be either complex RI or complex MA. We don't care because we know that both of those classes respond to the same messages, and therefore we can treat these generically as one interface and just program according to that interface. So we do create a particular class in order to return what you get when you add 2 numbers together, but we don't assume a particular class of the inputs. And in that sense, this is a generic function, add complex, because it doesn't assume that Z1 and Z2 are of a particular type. They could be either one of the types. And same goes for mul complex. We don't know which type Z1 and Z2 are, but we know they both have a magnitude and an angle, so we use that fact in order to use these messages, these attribute names, in order to get what we need, in order to construct their product. At which point, we can add complex numbers together. So 1 plus 2i plus the thing that you get at 2 pi over 2. So what is 2 pi over 2? Well, pi over 2 is a 90-degree angle, if you like to think of it that way. It goes straight up the y-axis for a length of 2, so this is 2i. So the result should be 1 plus 4i, which is exactly what we see, with a little rounding error. And what happens when we multiply I times something that has, and what happens when we multiply I times I? Well, we should get -1, because I is the square root of -1. So the way we get -1 represented to us is a vector of magnitude 1 in the negative direction. That's pi.